Welcome to Brain Vision.
Hi everyone, so what we're looking at today is a vertical piston cylinder with an initial volume of 0.01 cubic meters of steam. The initial temperature is 200 degrees Celsius. The piston and cylinder are such that the P is constant at 500 kPa. There is a supply line at 1 megapascal and 350 degrees C, which is closed when the volume inside the cylinder is equal to 2 times the initial volume. And assuming that there is no heat transfer, what we're asked to find is the final temperature and the mass that has entered this piston cylinder. So what we're going to do first is find the properties of our steam, looking at the thermodynamic tables, and what we find is that for an initial state of P1 and T1 equal to 500 kPa and 200 degrees C, we have an initial specific volume of 0.42503 meters cubed per kilogram, and we also find that we have an internal specific energy of 2,643.3 kilojoules per kilogram. And similarly, we're also going to find the incoming enthalpy of our supply line. So from those same tables, we can see that for a pressure of initial of 1 MPa and an incoming temperature of 350 degrees C, the incoming enthalpy is equal to 3,158.2 kilojoules per kilogram. Next, what we're going to do is define our system, which we're going to call the cylinder, and that's also the control volume because mass transfer is happening across that boundary. So when we do our mass balance, we'll see that the mass coming in minus the mass coming out is equal to the change in energy of the system, of the mass of the system. Now, there's no mass that's leaving, so this is 0, but we do have mass that's coming in, so we can simply say that Mi is equal to M2 minus M1. Now let's go ahead and do our energy balance. So we know the energy balance set is equal to energy in minus energy out is equal to change in energy of the system. Again, remember that we're neglecting heat transfer, so we can say that there's only energy coming in, and that's going to be equal to MIHI. But remember, we also have work, so minus WB out, we're going to call that boundary work, is equal to the change in internal energy of the system, so it's going to be M2U2 minus M1U1. Now I'm just going to bring the work to the other side, so we're going to say that MIHI is equal to M2U2 minus M1U1 plus WB. Now what I'm going to do is combine this energy relation with the initial relation we had with the mass balance, and just to remind ourselves that mass balance relation was Mi is equal to M2 minus M1. So what we can do now is put both of these equations together and just go ahead and plug in for Mi, and what that gives us is 0 is equal to WB minus M2 minus M1 HI plus M2U2 minus M1U1. Now remember, the boundary work is going to be given by this equation here. The boundary work is equal to state 1 to 2 of PdV. Now good for us that the pressure is actually constant, so we can just write this as P times V2 minus V1. And we know the pressure, and we know that the final volume is going to be 2 times the initial volume. We know the initial volume to be 0.01 cubic meters, so we can actually go ahead and solve this equation, and what this gives us is a boundary work of 5 kilojoules. Now we can also go ahead and find the initial and final masses in the cylinder. So we know that using the definition of specific volume, which is equal to total volume over mass, we can just go ahead and bring the mass to the other side and bring the specific volume into the denominator and say that initial mass is equal to V1 over specific V1, which is equal to 0.0235 kilograms. Similarly, for mass 2, we can say that mass 2 is equal to big V2 over specific V2, which is a quantity that we don't know yet. So what this is going to be is M2 is going to be equal to 0.02 cubic meters over V2. Now we can actually go ahead and take these quantities and plug this into our work energy relation that we have with mass. And what this ends up being is 0 is equal to that 5 kilojoules of work minus M2, which we said was 0.02 over V2, minus M1, which we know to be 0.0235 kilograms, times HI, which is the incoming enthalpy, and that's going to be 3.3158.2, plus M2, which again is 0.02 over V2, times U2, which is a quantity we don't know, minus M1, 0.0235, times U1, which is 2643.3. Now we do have an equation with two unknowns. So what we can do is just go ahead with trial and error, and what we find is that this equation is satisfied. This goes to 0 when T2 is equal to 261.7 degrees C and V2 is equal to 0.4858 meters cubed per kilogram. So right here, this is our final temperature. Remember, we're also asked to solve for the final mass of the cylinder. Actually, the mass that has entered the cylinder. So we know that M2 can be solved for by doing total volume 2 over specific volume 2. And these are quantities that we both know. So we can go ahead and say that M2 is equal to 0.0412 kilograms. And the mass that enters is going to be equal to M2 minus M1. And doing this calculation gives us a mass that is entered of equal to 0.0176 kilograms. And that's our final answer.